All right, so have you ever looked at like a rusty old car and wondered what the heck happened there? At like the atomic level.
Ah.
Well, that's what we're diving into today, how things fall apart, like literally at the atomic level.
Oh, wow.
Yeah, we're talking corrosion and degradation.
Right.
The processes that break down bridges, airplanes, even stuff inside our bodies.
Yeah, it's incredible.
And we're taking a deep dive into chapter 17 of this materials science textbook
Okay.
to tackle how metals, ceramics, and polymers all break down.
Mm,
And honestly, when I started reading about corrosion, it kind of blew my mind.
yeah.
It's like there are these tiny little wars happening on surfaces, all because of electrochemistry.
It is fascinating, right? It really is like these tiny little battles are happening all around us constantly.
Exactly. And luckily, we've got an expert here to help us break it all down.
Well, I'm happy to try to demystify some of it.
Okay, so let's get right to it. We've got these terms, oxidation and reduction.
Right.
What exactly are they, and how do they team up to cause all this corrosion damage?
So in the case of metals, corrosion is all about the movement of electrons.
Okay.
And you can think of oxidation like a metal atom getting robbed of its precious energy, those electrons.
Mm.
And this always happens at a specific spot called the anode.
Oh, okay.
But those electrons don't just disappear. They get picked up by another atom at a place called the cathode, and that's reduction.
So it's like a give and take.
Exactly. You
Yep.
can't have one without the other. It's this constant flow of electrons that drives the whole corrosion process.
So like a tiny electrical circuit happening right there on the surface.
A very good analogy.
And it just like in a circuit, I was reading that the type of metal really matters.
Oh, absolutely.
Some metals are more willing to give up their electrons than others.
Yes, exactly. Some are more generous with their electrons, you could say.
Right. So it's not just about being in a corrosive environment, but also who you're hanging out with.
Precisely.
Like, I was fascinated by this idea that some metals end up sacrificing themselves to protect others.
Yes. That's the concept of a galvanic couple. When you get two different metals together, and one becomes the hero corroding away so the other can stay safe,
It's like a buddy system for metals, but with way higher stakes.
that's one way to put it.
The textbook gave the example of galvanized nails. They coat steel with zinc,
Right.
and the zinc, being the more generous metal, takes the hit, saving the steel.
A perfect example. And we can actually predict which metal will be the sacrificial one using something called the galvanic series.
Oh, the galvanic series.
Yeah, it ranks metals by how likely they are to corrode when they're in seawater.
So, like, if you're building a boat, you better know your galvanic series.
It's definitely a handy tool for certain applications.
For sure. Okay,
Yeah.
so now we know which metal is going to corrode, but how do we measure how fast it's happening?
Right, so that's where we get into corrosion rate.
Right.
And one way to express this is as the corrosion penetration rate, or CPR.
CPR.
Yes, and it tells you how much material thickness is lost over time, usually in millimeters per year.
Oh, wow. So, like, how many millimeters of your car disappear each year?
Exactly, imagine that.
Makes you think twice about parking it outside.
Right.
So a higher CPR means faster corrosion.
Yes, precisely.
Okay, but what about this term polarization? That's where things started to get a bit fuzzy for me in the textbook.
Oh, polarization.
Hmm.
So polarization is essentially how the environment messes with the corrosion process.
Okay.
It shifts the actual corrosion potential away from the theoretical values we see in that galvanic series.
Huh.
Think of it like traffic during rush hour. It slows down how fast things can happen, even if everything's in place for a speedy reaction.
Okay, that makes sense. I can picture that. But why does polarization happen?
Well, there are two main types,
Right.
activation polarization and concentration polarization.
Mm.
Activation polarization is all about the slowest step in the electrochemical reaction. Imagine a narrow doorway at a concert.
Oh, yeah.
Even if everyone has a ticket, that bottleneck slows down how fast people can get in.
So even if a metal is eager to give up its electrons, there might be another step in the process holding everything back.
Exactly. Now, concentration polarization is a bit different. Okay.
It's about how fast the reactants, like those electron-hungry hydrogen ions, can actually get to the metal surface. Think of it like a crowded subway platform during rush hour. Even if people want to get on the train, if they can't reach the doors because of the crowd, things slow down.
So both types of polarization can limit how fast corrosion happens, making things less predictable than just looking at that galvanic series.
That's right. And we can actually use those principles to predict corrosion rates using something called polarization curves.
Oh, polarization curves.
Yeah, they basically map out how the voltage changes with the current.
Okay.
It's A bit technical.
Yeah.
But the key takeaway is that we can use science to understand and even predict how fast a material will corrode.
So we're not just throwing darts in the dark here.
No, not at all.
We can use this knowledge to make smarter choices about materials and design.
Precisely. And that's incredibly important for everything from building safer bridges to making more durable medical implants.
That makes sense. But we've been focusing a lot on metals here.
What about other materials like ceramics and polymers?
Good question.
Do they corrode in the same way?
Well, ceramics are kind of unique. You see, they're already in a very stable state, almost like they've already been corroded in a sense.
Right.
So this makes them incredibly resistant to further degradation, especially at normal temperatures.
So they're like the strong, silent type.
You could say that, though, they've already been through their rebellious phase.
I like that analogy.
Yeah.
But they can still break down under certain conditions, right?
You're right, they're not completely invincible.
Okay.
Extremely high temperatures or harsh chemicals can still cause them to degrade. Think about the tiles on the space shuttle, for example.
Oh, yeah.
They have to withstand incredible heat and corrosive exhaust gases.
So they're tough cookies.
They are.
Okay, so what about polymers? How do they fall apart?
Well, polymers are a bit different. They degrade through a combination of physical and chemical changes. We actually call this degradation rather than corrosion because it's not primarily driven by those electrochemical reactions like we see in metals.
So different materials, different ways of falling apart.
Exactly. Different mechanisms at play.
Okay, and polymers, they mainly degrade through two processes.
Yeah.
Swelling and dissolution and bond rupture.
Right.
So let's break those down. What exactly happens during swelling and dissolution?
So swelling is when a liquid or a solute seeps into a polymer, causing it to expand and weaken.
Like a sponge soaking up water.
That's a good analogy. At a much tinier level, of course.
Right. And then dissolution is like swelling on overdrive, where the polymer completely dissolves in the liquid.
Exactly.
Like if you leave a plastic container in acetone.
Oh, yeah. Depending on the type of plastic, it might just vanish.
So no storing nail polish remover in flimsy containers.
Probably not a good idea.
All right, good to know. What about bond rupture? Is that what happens when plastic cracks or becomes brittle?
Exactly. It's when those long chains of molecules that make up the polymer get broken.
Okay.
This can happen because of radiation heat or even certain chemicals.
So lots of potential enemies for polymers. Let's start with radiation. How does that cause those bonds to break?
Think about how plastic garden furniture fades and becomes brittle after years in the sun.
Oh, yeah.
That's UV radiation doing its work.
Wow.
Those rays have enough energy to break the chemical bonds holding the polymer together. It's a big problem for things like spacecraft, too, which are constantly bombarded by cosmic radiation.
I hadn't thought about that. So we need special polymers for those extreme environments.
For sure.
Okay. And what about chemical reactions? How do they cause bond rupture?
One classic example is what happens to rubber tires that are exposed to ozone. Ozone, which is a common air pollutant, attacks the rubber molecules, leading to cracks, especially when the tires are under stress.
So even tiny amounts of pollutants can have a big impact.
They can. It's amazing how these seemingly small things can wreak havoc at a molecular level.
It really is. And finally, what about heat? How does heat cause bond rupture?
Well, heat makes molecules vibrate faster, and if it gets hot enough, those vibrations can actually break chemical bonds.
Oh, wow.
Ever smelled burning plastic?
Oh, yeah.
That's PVC breaking down and releasing nasty corrosive gas.
Yikes.
Different polymers have different breaking points, so we need to be mindful of the temperatures we expose them to.
Makes sense. So it's like each type of material has its own Achilles' heel.
It seems that way.
But knowing those weaknesses is how we learn to protect them, right?
You're absolutely right. Understanding how and why materials degrade is the first step in learning how to prevent it, or at least slow it down.
And speaking of preventing it, are there ways to fight back against this inevitable breakdown?
Absolutely.
Our textbook mentioned a few strategies,
Yeah.
like choosing the right material.
Oh, that's one of the most fundamental ways. If you know the environment a material will face, you can pick the one most likely to survive.
Okay.
Think back to the galvanic series. You wouldn't want to put two metals with vastly different tendencies to corrode in direct contact with each other.
So it's like picking the right tool for the job, just like in any other field.
Exactly. The right material for the right application.
Okay, so what other strategies do we have?
Well, sometimes we can actually modify the environment to make it less harsh.
Oh, interesting.
Lowering the temperature or slowing down a corrosive fluid can make a big difference. We can also add inhibitors to the environment, which are like tiny bodyguards for the material.
Inhibitors?
Yes. They work by either neutralizing those corrosive agents or by forming a protective layer on the material surface.
So it's like we're building a fortress around the material.
Exactly, shielding it from attack.
I like it. Are there any other ways to prevent corrosion?
Smart design can play a big role.
Okay.
Avoiding sharp corners or crevices where corrosive agents can accumulate can help a lot. Also, ensuring good drainage can prevent those stagnant areas where corrosion loves to party.
Corrosion loves to party.
It does.
So it's not just about the material itself, but about how we use it and the environment we put it in.
Precisely. It's a holistic approach.
I like that. And of course, we can't forget about coatings.
Oh, coatings are essential. They act like a physical barrier between the material and the environment.
Right.
We can use metallic coatings like galvanization, where we apply a layer of zinc to steel, or non-metallic coatings like paint ceramics or even polymers.
So many options.
Yeah.
But I'm particularly fascinated by this concept of cathodic protection.
Oh, cathodic protection.
Yeah. It sounds almost heroic, like we're actively defending the material from attack.
It is a bit heroic.
So how does it work?
Cathodic protection is all about making the metal we want to protect the cathode in an electrochemical cell, essentially preventing it from corroding.
Okay.
And we can do this by using a sacrificial anode, which is a more reactive metal that's electrically connected to the protected metal. The sacrificial anode corrodes instead, like a noble warrior taking one for the team.
A true metal martyr.
Indeed.
Yeah.
And the other method is to use an impressed current.
Okay.
This involves connecting the metal to a power source, which forces electrons into it, making it a cathode and preventing oxidation.
So we're basically giving the metal a boost of electrons to keep it happy.
Exactly, like a little energy drink for the metal.
I love these analogies. So we use this method to protect things like pipelines and ships, right?
Exactly. Large-scale structures that are constantly exposed to corrosive environments.
Okay, so we've got a whole arsenal of weapons to fight back against corrosion.
It's an ongoing battle.
It is.
Yeah.
From picking the right materials to manipulating the environment to using clever coatings and even enlisting sacrificial anodes.
It takes a multifaceted approach to win this war.
Well said. Now, we've talked about corrosion in liquids, but what about corrosion in the air? That's where oxidation comes in, right?
Ah, yes, oxidation. So it's simply a metal reacting with oxygen,
Okay.
whether it's in air or water. Think of the greenish patina that forms on copper statues.
Oh, right. So oxidation isn't always a bad thing.
You're right. Sometimes it's even desirable. Like that patina, it can be quite beautiful.
Yeah, it can. But other times it's very destructive.
That's true. The key is understanding how that oxide layer that forms on the metal behaves.
Okay, so how do we know if an oxide layer is good or bad?
Well, one important factor is the Pilling-Bedworth ratio. The Pilling-Bedworth ratio, it compares the volume of the metal to the volume of the oxide it forms.
Okay.
If the ratio is close to 1, the oxide layer tends to be dense and protective, like a good coat of armor.
I see.
But if the ratio is much different, the oxide might be flaky and basically useless, offering very little protection.
So remembering that copper patina we talked about.
Yeah.
That's a good oxide, a protective one.
Exactly. But some metals have a bad ratio, like potassium. Their oxide is flaky, useless. Knowing this ratio helps us choose the right metal for the job.
Oh, for sure. And does the Pilling-Bedworth ratio also influence how fast a metal oxidizes?
Absolutely. Sometimes the oxidation rate slows down as the oxide layer grows thicker. Other times it continues at a constant rate or even slows down dramatically over time.
It's fascinating how these seemingly simple reactions can have so much complexity hidden within them. It's like a whole new world is unfolding at the atomic level.
That's the beauty of materials science. There's always more to discover. There really is. And that complexity is what makes this field so fascinating. There's always more to learn, always new ways to kind of outsmart these pesky degradation processes.
Speaking of outsmarting, you mentioned earlier that we can sometimes use these processes to our advantage. How is that even possible?
Well, one example is chemical etching. It's a technique that uses controlled corrosion to create intricate patterns or surface features on materials.
Oh, wow.
So by carefully selecting the chemicals and the conditions, we can essentially sculpt the material, removing tiny bits with incredible precision.
So it's like we're turning the enemy's weapons against them.
Exactly. We're harnessing the power of corrosion for our own purposes.
That's pretty ingenious. What kind of applications does this have?
Well, think about microelectronics, those tiny circuits on computer chips.
Yep.
They're created using chemical etching. It's also used in art restoration to carefully clean and restore corroded metal artifacts, bringing historical treasures back to life.
Wow, that's amazing. So we're not just fighting degradation, we're actually funneling it to create some of the most advanced technologies we have.
It really highlights the dual nature of these processes. They can be both destructive and creative.
Okay, so we've talked about the different types of materials, how they degrade, and even some ways we can prevent or control these processes.
Right.
But are there any real-world examples of corrosion or degradation that you think really highlight the importance of understanding these concepts?
Oh, absolutely. There are countless examples, but one that always comes to mind is the collapse of the Silver Bridge back in 1967.
Oh, yeah. I remember reading about that. It was a huge tragedy.
It was. The bridge spanned the Ohio River, and it collapsed suddenly during rush hour, sending dozens of cars and people plunging into the icy water.
Horrifying. What caused such a catastrophic failure?
The investigation revealed a tiny crack in a key structural component called an eye-bar, and this crack had been growing slowly due to stress corrosion cracking.
That's corrosion cracking.
Yeah, where you have both mechanical stress and a corrosive environment working together.
Right. And in this case, the corrosive environment was simply the humid air over time. That combination of stress and corrosion caused the crack to grow larger until the eye bar finally gave way.
A tiny crack leading to such a huge disaster. It's a stark reminder that even seemingly small flaws, if left unchecked, can have devastating consequences.
Absolutely. And it underscores the importance of regular inspections and maintenance to catch those problems early on.
For sure. Are there any other examples of corrosion-related failures that you find particularly noteworthy?
Another one is the Aloha Airlines Flight 243 incident back in 1988.
Oh, I vaguely remember hearing about that one. What happened?
A Boeing 737 experienced an explosive decompression in mid-flight, tearing off a large section of the fuselage.
Oh my gosh.
Thankfully, the pilots managed to land the plane safely, but one flight attendant was tragically lost.
That's terrifying. What caused the fuselage to tear apart like that?
The main culprit was metal fatigue, where repeated stress cycles weaken the material over time.
Right. But those fatigue cracks were made worse by corrosion, especially in the joints where the fuselage panels were riveted together.
So again, we see how corrosion can team up with other factors to cause catastrophic failures.
Exactly. It's often a combination of factors that leads to these kinds of events.
These stories really underscore the importance of thorough inspections and maintenance to catch those problems early on.
They do. Early detection is key to preventing these kinds of disasters.
And as we develop new materials and technologies, we need to be even more vigilant about understanding how they might degrade over time and what steps we can take to mitigate those risks.
Couldn't agree more.
So I'm curious about the future of this field. Are there any areas of research or innovation that you find particularly exciting in terms of preventing things from falling apart?
One area that's generating a lot of buzz is the development of self-healing materials.
Self-healing material.
Yeah, imagine materials that can actually repair themselves when damaged.
Like our bodies heal from cuts and bruises.
Exactly. It's like science fiction becoming reality.
That sounds incredible. How does it even work?
Well, there are several approaches being explored.
Okay.
One strategy is to embed tiny capsules filled with a healing agent within the material. When a crack forms, those capsules rupture, releasing the healing agent, which then reacts to seal the crack.
So it's like a built-in first aid kit for the material.
A very apt analogy.
I love it. Are there any other ways to create these self-healing materials?
Another promising approach uses materials that can change their shape or properties in response to external stimuli.
Okay.
For example, some polymers can remember their original shape and revert to it even after being deformed. This shape memory effect could be used to design materials that automatically close up cracks or adapt to changing conditions.
Wow, so we're moving beyond simply preventing corrosion and degradation to actually creating materials that can undo the damage that's already been done.
It's a paradigm shift in material science.
It's like giving materials superpowers.
It really is.
Yeah.
And it has the potential to revolutionize many industries, from infrastructure and transportation to electronics and even medicine.
I can't wait to see what the future holds for these self-healing materials.
Yeah.
It sounds like we're on the verge of a new era in material science where things might not be as prone to falling apart as they are now.
It's a future worth striving for, and it's a testament to the ingenuity of scientists and engineers who are constantly pushing the boundaries of what's possible.
This has been an incredible deep dive into the world of materials degradation.
I agree.
From those tiny electrochemical reactions to the grand challenges of preventing catastrophic failures, it's been an eye-opening journey.
It has.
And we've covered a lot of ground. But before we wrap up, I want to leave our listeners with a final thought-provoking question.
Okay, I'm listening.
Knowing what we now know about the various ways materials break down, what steps can you, our listener, take to protect the materials in your own life?
Yeah.
Think about your car, your appliances, even the clothes you wear. What simple changes can you make to prevent or slow down those degradation processes?
That's a great question.
It's a challenge we can all take on armed with the knowledge we've gained today.
It's a great question to think about. Even small actions can make a big difference, like just keeping things clean and dry.
Exactly. And being mindful of the materials we choose in the first place, like opting for more durable options whenever we can.
Right. Choosing wisely from the start.
Yeah. Well, I think we've really thoroughly explored the ins and outs of materials degradation, from those tiny electrochemical battles to the fascinating ways polymers break down.
Yeah, it's been a really comprehensive deep dive.
It has been incredibly eye-opening for me, and hopefully for our listeners as well.
I agree. It's always rewarding to share these insights and spark some curiosity in others.
Before we sign off, though, there's one more concept from the textbook I wanted to touch on: the kinetics of oxidation.
Oh, yeah, the kinetics.
It's all about how fast those on-side layers form. And our textbook mentioned these three main rate laws that govern this process: linear, parabolic, and logarithmic.
Right, those are essential for predicting how quickly oxidation will proceed.
Okay, so let's break those down. What does it mean for the oxidation rate to be linear?
So a linear rate law means the oxide layer grows at a constant speed regardless of how thick it already is.
Okay.
This usually happens when the oxide layer is porous or flaky and doesn't do a good job of blocking oxygen from reaching the metal.
So not a good thing.
Not ideal. It's like trying to fill a leaky bucket. The water level keeps rising at the same rate no matter how much water is already in there.
I see. So what about parabolic rate laws? How are they different?
A parabolic rate law means the oxidation slows down as the oxide layer gets thicker.
That's better.
It is. That's because the oxide layer starts acting like a barrier, making it harder for oxygen to diffuse through and react with the metal.
Makes sense.
It's like trying to push a shopping cart through a crowded store. The more stuff you have in the cart, the harder it gets to move.
A very relatable analogy.
Yeah.
All right, and the last one, logarithmic rate laws. How do they work?
Logarithmic rate laws are the slowest of the three. The oxidation rate drops off dramatically as the oxide layer thickens. This often happens at lower temperatures and is associated with those superprotective oxide layers we talked about earlier.
Right.
They're so good at blocking oxygen that the oxidation practically grinds to a halt.
So a very strong shield against oxidation.
Exactly.
I'm starting to see how understanding these rate laws can be really crucial for designing things that can withstand harsh environments.
Oh, absolutely. For example, if engineers are designing a jet engine that operates at extremely high temperatures, knowing the oxidation rate law for the materials they're using is critical.
Yeah.
They need to make sure the components won't oxidize too quickly and compromise the engine's performance and safety.
That's a good point. It's
Yeah.
amazing how much complexity is hidden within these seemingly simple processes.
It really is. There's a whole world happening at the atomic level.
Well, this has been a truly fascinating deep dive into the world of materials degradation. It's amazing to think that these tiny invisible processes can have such a huge impact on our everyday lives.
It's a reminder that the world is much more complex and interconnected than we often realize.
Well said. Thank you so much for sharing your expertise with us today.
It's been my pleasure.
And to our listeners, we hope this episode has sparked a bit of curiosity in you. The next time you see a rusty old car or a cracked piece of plastic, think about the intricate processes that led to that breakdown. And maybe you'll even be inspired to explore the world of material science a bit further. Until next time, keep those electrons in check. And remember, everything eventually breaks down, but understanding how and why is the key to making things last a little bit longer.